Good evening and welcome back to the University of California Observatory's Living Room Lecture Series. If you have been joining us for all of our events, the Friends of Lick's Bolo Family Dinners, our Ask an Astronomer series, and of course the Living Room Lectures, you have heard from some of our supernova hunters, our UCO leadership, and we'll now hear from one of our exoplanet hunters. Joining us live from his living room, or wherever he could find a quiet space from his adorable children, is UCSC faculty member Dr. Andy Skemer. He will describe how we image planets, why we image exoplanets, and where the field is heading as we develop technology that will soon be capable of detecting biosignatures on habitable planets. Thank you so much, Andy, for joining us tonight.
Thank you. And here, let me share my PowerPoint. Okay, can everybody see that? Good. Thanks so much for joining us. My name's Andy Skemer. I'm an associate professor at UC Santa Cruz. I'm going to be talking about how we image exoplanets, which are planets that orbit other stars besides our sun. One of the things about this talk is that the technology involved in how to image an exoplanet is really what's featured here. It's a very difficult problem to see something very, very faint that's very close to something very, very bright. And so this intro image is of the Keck Observatories. Those of you from the Bay Area may know about Lick Observatory or have visited there. And Lick Observatory is operated by University of California Observatories. But actually our flagship telescope is out in Hawaii, where the weather is a little bit better and there are fewer streetlights. So these Keck telescopes are each 10 meters in diameter, the biggest telescopes in the world. You can sort of get a feel for it if you look at the road right here where my mouse is. And I think those are probably a couple of cars right here. So these are gigantic scientific machines that are perfect for imaging exoplanets. So let me start out with this image. And I want all of you to think about and maybe guess where this image was taken. And because you're at home, you can shout it out loud and you won't disturb anybody else's thoughts. So take a second, shout it out loud. All right. Some of you may think that this is the San Francisco Bay Area with the ocean right here and rivers and clouds. But it's actually an image of Titan, which is a moon around the planet Saturn. And it also has lakes and it has rivers and it has clouds, but they're not made of liquid water. They're made of methane and ethane, hydrocarbons. So I like to show this image because people think about extrasolar planets as being something similar to the planets in our own solar system, but actually our own solar system just has an incredibly diverse population of planets and moons also. And this was taken by the Huygens probe, which actually landed on the surface of Titan. And there's going to be a new mission to Titan soon with a quadcopter that's going to go flying around. So there's a ton that we can learn about planets and moons in our own solar system. But we'll never take an image like this of an exoplanet. Exoplanets are too far away. You just can't get this sort of resolution on an exoplanet. So this is more what we hope to be able to do with exoplanets. This is Carl Sagan's famous pale blue dot image of the Earth. And the Earth is right here. Earth is 1 pixel wide on this image. And that is the best we'll ever be able to do with exoplanets. This was taken by Voyager while it was in our solar system. So you can imagine if you're looking 2 or 3 solar systems over, Earth is going to be, the Earths in those solar systems are going to be even further away. They're going to be even smaller. So a single point of light is the best we can do on exoplanets. Now, the reason we're interested in exoplanets is because there are all sorts of different kinds. There may be other ones like Earth. So we really want to be able to see these things around other stars. It's just, if we want to learn what's going on, we're going to have to really work for it. We're not just going to get a nice, pretty picture. So if you look at this pale blue dot, and you're an alien astronomer from another solar system, and this is just the most amazing image you've ever taken. you might be able to tell. The fact that it's blue might tell you that there are liquid water oceans reflecting Rayleigh scattering from the Earth's atmosphere. The fact that it's pale blue might tell you that there are also some white clouds on it that are muting the deep blue from the ocean. If you were to watch this pale blue dot for 24 hours and keep watching it, you would see that it gets brighter and fainter as continents and oceans come into your field of view, and the same ones come into your field of view on every 24 hours. You might notice some additional variations on top of that, which would be the clouds and the weather on the Earth. So you can learn a ton from an image like this, even though it's just a single dot. One thing about this image, the fact that it's pale blue is important. It's not a black and white image. This is a color image of Earth. And so in order to make an image like this, Carl Sagan and his collaborators used 3 different filters, wavelengths, on Voyager. And they made a 3-color image. So just like your digital camera has red, green, and blue pixels, they did the same thing to make this pale blue dot image of Earth. When you're an astronomer and all you've got is a single dot, you've got to work even harder than that. And so the eventual goal for understanding exoplanets is more than just 3 filters or 3 wavelengths. It's to get a spectrum of an exoplanet. So if you were to take this light from the pale blue dot and you put it through a prism, the prism disperses the light into a continuous spectrum, otherwise known as a rainbow. So you get all of the different wavelengths from purple to red. Each one of these can tell you something different about the exoplanet. So instead of having 3 wavelengths, you can get almost as many as you want. This is what a spectrum looks like to an astronomer. So this is actually a spectrum of the sun, not the Earth. But you'll see that you've got sort of purple and blue at the bottom. And as you work your way up the spectrum, you go to green, yellow, and red, the colors of the rainbow. And in the spectrum, you'll see some dark lines, which I'm putting my mouse on. Hopefully you can see that. Each of those dark lines in the sun is the spectral signature of a different atom in the sun's atmosphere. And astronomers, you look at a picture like this and you can identify the atoms. This right here in the orange, these 2 dark ones, those are sodium. So you can look at this and see the spectral fingerprint and figure out what a star is made out of. And that's been the bread and butter for astrophysics for the last 100 years. Looking at stars, looking at galaxies, but not just taking images, taking spectra and really learning what things are made out of. If you took the pale blue dot and took a spectrum of that, this is what the Earth spectrum looks like. And now I'm showing this to you in a different way. So I'm showing wavelength on the x-axis. This is blue light on the left-hand side of the panel, red light over here, and then everything else is infrared light, which is where most of the action is. If you look on the y-axis right here, you're seeing how much light is coming back. So wherever you see these deep lines right here, those are like the black lines on the previous plot. So if you were an alien astronomer and you got this miraculous spectrum of Earth, you could look at this and you could identify, okay, these lines right here, these really deep ones, those are H2O, water vapor actually. And if you measure the depth of these lines, you could figure out how much water is in the atmosphere of Earth. If you really, really carefully measured the shapes of the line, you could figure out how high the water is in the Earth's atmosphere. You would see this line right here, oxygen. On the Earth, oxygen is created by photosynthesis of plants. So that is what is known as a biosignature. It's evidence that there is life on Earth. A lot of people think that you might be able to get oxygen without life, but if you see oxygen and methane, which is over here, the 2 of those together don't exist easily without life. The methane would go away very quickly. There's CO2, you can maybe understand something about our greenhouse gases. And then up here, this is very important. This is what's called the red edge. You might think that plants reflect a lot of light at green, which is true, but if you had infrared eyes, you would see that they reflect much more light in the infrared. And there's sort of a sharp feature in the spectrum of plants that doesn't come from these sort of ordinary molecules here. that we think might be a way that we can detect plant life or something like that on other planets. So this is really the goal when we're trying to understand other planets. It's with something like spectroscopy and looking at these individual lines. And if we get there, if I take a spectrum of like this of another planet, you know, I get a Nobel Prize. So it's easy to come up with the idea, and the hard part is the technology. So I'm gonna talk a little bit about the technology and why it's so challenging to image exoplanets. This is an image from National Geographic. They had a nice article that explained the technology and why it's so difficult to image an exoplanet. And the analogy that they used is that imaging an exoplanet is like looking for a firefly next to a searchlight. Earth is 10 billion times fainter than the sun, and a firefly, I guess, is about 10 billion times fainter than a searchlight. But it's even that's too easy. The searchlight has to be really, really far away, and the firefly has to be really close to it. So actually, they said it's like a firefly next to a searchlight from 3,000 miles away. And then they had this image, which I think is funny because there's no way a firefly is that bright. They had to Photoshop that a little bit, which is not surprising. If National Geographic had cameras that could see something 10 billion times fainter than a searchlight, they could point that at a star and image an Earth-like planet. So this is a really hard optics problem. The first thing that you need to image a planet is, well, I guess I have to say a little bit about what a planet image looks like. So this right here is a star, and this companion right here, it's actually another star. It's just this star is much brighter than this star. And when you take an image of a star, technically it's a point of light, but your optics, the Earth's atmosphere, everything ends up blurring it out. This is so many photons right here, it's just impossible to squeeze them all into a tight area. So in this case, the bright star is 5,000 times brighter than the faint star. Remember that for an Earth-like planet, we need to get to 10 billion. So this is much easier than the problem that we eventually have. And the separation, because they're very close together, that's another problem. This star is 7 arc seconds away from the bright star. So I can't see all of you, but you're gonna have to, I'm gonna ask you to do something at home. So take your thumb and hold it out at arm's length. Natasha's gonna be watching to see that you're doing this. So if you look at your thumb at arm's length, it is about 1 degree apart, across. And an arc second is 1/3600th of a degree. So basically, if you're looking at this particular image, that companion is 1/500th of the width of your thumb, and it's 5,000 times fainter than the star. So that's a really difficult thing to do. What we have to do is concentrate the light more. And so the image on the left is from a ground-based telescope, and the image on the right is from the Hubble Space Telescope. And one of the things that makes the Hubble Space Telescope so special is that it's above the Earth's atmosphere, and it takes really, really, really sharp images. So this is the same system, same brightness ratio, but what's happened is that the Hubble Space Telescope is able to really concentrate the light of that main star, and then that makes it easier to see the companion. There's less glare from the main star on top of the secondary star. So that's really the goal here. We're trying to concentrate the light as much as possible. And there are 2 things you have to do to concentrate the light. The first is that you need the biggest telescope that money can buy. Or technology can build for that matter. So this is the Keck telescope that I showed you on the first slide. And on the right is Jerry Nelson. Jerry Nelson was a professor at UC Santa Cruz. He passed away a few years ago. But when people were trying to build bigger and bigger telescopes, he figured out that instead of building one giant mirror, you could synthesize a mirror by putting together a bunch of smaller mirrors. And so that's what he did to build the 10-meter Keck telescope. And now this is a strategy that a lot of people use. And so the James Webb telescope, which is launching in 2021, fingers crossed, uses this technology as well. It turns out that the sharpness of the image that you can make is limited by the size of the telescope. It's a quantum mechanical thing called diffraction. and you can make things, it's proportional to the wavelength of light divided by the diameter of the telescope. So if you make a telescope that's twice as big, you can make your light concentrated twice as much. So that's one of the things you need to make a really sharp image. The second thing you need to do is you need to deal with atmospheric turbulence. So unfortunately, this is something that blurs out images. If you've ever driven on a hot day and looked down a highway, you'll see some sort of bubbling air coming up from the highway, heat waves, some people call them, and they're blurring out the image in the distance. So if you're looking at a distant car, you'll see it sort of bubbling around. I'm going to show you a video of this, and this is the best video I could find. You're going to have to ignore, oh, I hope the sound doesn't come out. Yeah. You're going to have to ignore the frozen turkey being dropped into the turkey fryer. Okay, so if you look at the fence, you'll see all of this bubbling turbulence happening behind you. And if you look at one of these spots on the fence, it's moving around. And you can imagine if you took a long image because you were trying to see a really faint planet, it would be moving around, and that would make it hard to see. If the star would be moving around, the glare would be moving around, and that would make it hard to see the planet in the background. So here's what this looks like for a star. So again, the star, if we didn't have to deal with turbulence, it would be 1 pixel. But because of the turbulence, it's this big blob on the sky. This is what images actually look like when you're at a telescope. And what I'm going to do is I'm going to play this video of the star. And this is what the Earth's atmosphere is doing. It's wobbling things around. And then I'm going to turn on something called adaptive optics, which is the technology that we use to correct the turbulent imaging in the Earth's atmosphere. So here's this video. You can see it bubbling around. If there were a planet next to this star, we wouldn't see it. Boom. There's the adaptive optics. So the adaptive optics turns on. I'll play it again. When the adaptive optics turns on, boom, it sharpens up that main star. Turns out that main star was actually a binary. You couldn't tell that because it was so blurry before, but the adaptive optics really sharpened up the image. And the other thing you can see is there's something really faint down there. So the adaptive optics does 2 things. It concentrates the light of the star and gets it out of the way of the planet, and it actually makes the planet brighter as well. So when you build these really big telescopes, the bigger the telescope, the sharper the image. But on Earth, that's not completely true. If you build a bigger telescope, it doesn't make sharper images unless you use adaptive optics. You can take a nice backyard telescope and make an image, you know, almost as sharp as Keck. But if you have adaptive optics, that's what allows you to take advantage of that really, really big telescope. So you need both of those things. Here's how adaptive optics works. So you have light coming from the star. And if it were coming from the star, it spreads out like a circle, and eventually it looks like plane waves when it's coming towards the telescope. So you've got plane waves coming. They hit the Earth's atmosphere. The Earth's atmosphere has that bubbling turbulence going on, and it distorts the wavefront into this wrinkled up shape. The wrinkled up shape goes through the telescope optics, and it stays like a wrinkled like shape. And when you take an image of something like that, you get that blurry thing that we saw on the previous page. So what adaptive optics does is part of the telescope includes a deformable mirror. And the job of this deformable mirror is to exactly cancel out the distortions in what should have been a plane wave and restore the plane wave. So this deformable mirror changes shape every time this plane wave changes, the distorted wavefront changes, and then it images it into the instrument, and that's how you get this nice adaptive optics image. The way that you have to do this is you have to measure the shape of this wavefront, which changes about 1,000 times per second. So 1,000 times per second, you measure the shape of the wavefront. You have a computer that quickly calculates how much voltage to put on each little actuator on this deformable mirror and changes the shape of this deformable mirror 1,000 times per second. And that's the only way that you can make an image like this. So this is an amazing engineering accomplishment to be able to cancel out the turbulence from the Earth's atmosphere. Here is what this looks like. These are images of a star I took with the large binocular telescope. And what you'll see, the adaptive optics is on. And you'll see there's some glare from this star, but it's very stable. It mostly stays the same shape over time. And that means the adaptive optics is working really well. Now, if you look at this more closely, The star is mostly staying the same, but there is something changing about it. So watch the video and see if you see anything that's changing about the star. Play it one more time, and this time I'll point it out. There's a dot right there, and it's rotating around the star. Move my mouse out of the way. Right there. So that's what we're looking for. The star is staying the same, but there's something moving around it. Now, that's what the raw images look like off of the telescope. Then the astronomer takes this back to their office, and after about 4 months worth of image processing and linear algebra, you can remove the starlight really, really carefully. And here's what this exact same data set looks like after I've removed the star as best as I can. And this really did take me several months of work to remove. And now you can see that dot really easily, right? And there's also a dot here and a dot here. And if you've been looking at these for a while, there's a dot over here. It's hard to see. There it is. Now I'm going to help your eye by speeding up this video, and then I think you'll see it. So here you go. So now you should see when I speed it up, there are 4 little dots rotating around the star that I've removed. And those are exoplanets. That's what we're looking for. Okay, if I take all of that data and stack it together, I get an image like this. This is what a 4-hour exposure with a really powerful adaptive optic system looks like. And you can see 4 planets around this star. This is the HR 8799 star. And these are planets B, C, D, and E working on your way in. All of these planets are about the size of Jupiter, but they're much more massive. They're maybe 5 times more massive than Jupiter. So they're gas giants. And the closest one is about 20 astronomical units compared to 5 astronomical units for Jupiter. So this is sort of a scaled up solar system compared to our own. But this is what we've been working so hard to do. This image, again, it took 4 hours with one of the biggest telescopes in the world with really sophisticated instrumentation. And I was so excited when I got this, and it's just getting one wavelength on these planets is enough to do great science. But I went back to the time allocation committee and said, all right, I did it with one wavelength. Can I do it with some more? And so then I went back, and even though one wavelength takes 4 hours, I went and did 6 of them. And there was a little bit less time on each one, so it's harder to see the planets, but here you can at least see 2 of them very easily in these images. And so now I have sort of like a multicolor image. So when I showed you that pale blue dot image and I said Carl Sagan had 3 wavelengths and made an RGB image, same thing here, we have 6 wavelengths. And so now we can really start to figure out a little bit about what's going on. But 6 wavelengths isn't the goal. The goal is a spectrum like we want to get for Earth someday. So the pale blue dot is fine, and that's the first step, but the goal is a spectrum. So I'm going to tell you a little bit about this technique that I'm using to get spectra of exoplanets. This is called hyperspectral imaging. Astronomers sometimes call it integral field spectroscopy, but everywhere else, people call it hyperspectral imaging. And the idea is that you're trying to take an image at every wavelength, or conversely, you're trying to take a spectrum of every pixel, and whichever pixel has the exoplanet on it, you got a spectrum of the exoplanet. So that's the goal. You make these data cubes. This is used in a ton of different fields. So for sure, one of the places it's used is remote sensing. You get a spectrum of every pixel of whatever you're looking at on Earth. You can see water, you can see different types of rocks and different types of foliage. And so satellites can be used to learn a lot. Used in food processing. So if you have a machine that shells a whole bunch of pistachios and you want to pick out the nuts and throw away the shells, you can take a spectrum of everything in this image, and it turns out the shells have one spectrum and the pistachios have another, and then the machine can learn to pick out the right things. It's also good, by the way, if one of the pistachios or whatever food you're looking at has some sort of is rotten or something's wrong with it. You can pick that out and throw that away. So this is used pretty ubiquitously in food processing. It's used in pharmaceuticals. So all these pills look like little white pills, but they have different chemical compositions, and it's very important that you can tell them apart. So they will image packages of pills to make sure that they're all the right kind. And here you can see two different spectra of different pills. One turns up as red and one turns up as green. Another thing it's used for is looking at emissions. So for example, if you have a factory and you want to see what types of gases are being emitted from your factory, and where they're being emitted from and what direction the wind is blowing them, you can take a hyperspectral image, and then, I think in this case, the purple's something like sulfur fluoride or something, and then this is methane. And so you're trying to figure out where the bad gases are going and whether they're leaking from everything. So this is used a lot in a lot of different fields. So in astronomy, we're always trying to take we don't have bright sources. We're looking at these very faint planets. We have to build very, very customized instruments that allow us to see, very, very faint things. And so we build these things from parts. This is the way that I do this. So you image whatever you want to look at, in this case, a galaxy, onto a two-dimensional array of little lenses. And each lens takes whatever part of the field you're looking at and focuses it into a little spot. Then you take that prism that I showed you early on that you can use to make spectra, and you put a prism behind these spots, and you rotate the prism in just the right direction so that you can get a spectrum of every pixel, and those spectra don't overlap. So that's how we do integral field spectroscopy in astronomy. I built an instrument to do this called AILS. This is a prototype instrument to show that this sort of thing works. And here is an image of Io, which is the innermost moon of Jupiter, right here. It's this circle. And you can see in the zoom in that every pixel is a little spectrum. And those spectra don't overlap, so I can separate them. If I take the bottom pixel in each one of these spectra, do some image processing, I can make a 2.8 micron image by just taking the bottom pixel of each one of these spectra. And if I work my way up the spectrum, I can get 2.9, 3.0, all the way up to 4.2 microns. So this is a 2-second exposure on Io, and then I do a bunch of linear algebra and convert it into this. So now I have images of Io at all of these different wavelengths. And if you look at the short wavelength end up here, I'm looking at reflected sunlight off of Io. And as you look at longer wavelengths, you can see this volcano. Io has volcanism. It's turning on, and when we use this to measure the temperatures of these volcanoes and try to understand the interior of Io. So that's sort of the prototype instrument. And now I'm working with Keck Observatory to build the instrument that we really want for imaging exoplanets. So it's called SCALES. That is a model of it. It's currently under construction at University of California Observatories. And SCALES is an exoplanet hyperspectral imager. It's meant specifically for taking spectra of exoplanets. And it really optimizes everything that we can do. We use the biggest telescope in the world. It's on an incredible site where the sky is really dark in the infrared, which is important because we look at these planets in the infrared. And unlike those images I showed before, where I struggled to get one image of an exoplanetary system, and then I struggled to get 6 images of an exoplanetary system, in one shot, this instrument will take 1,000 different images, 1,000 different wavelengths of extrasolar planets. So that's the dream. Now, this isn't real data yet. This is a simulation of what SCALES will do. And so I'm just scanning through all of these different wavelengths here. Each of these is a different wavelength image of an exoplanet. And if I just look at this one right here and all of the different wavelengths, I get a spectrum of that exoplanet. I'm only showing you about 70 wavelengths right now, whereas we hope to be able to do 1,000 with the final instrument. But in any case, I mean, 70 wavelengths, 1,000 wavelengths, it's a huge step forward for understanding exoplanets. So to show you how this has evolved during my career so far, back in 2012, I published one image with 4 planets of an exoplanetary system. It's a very nice image, but at the end of the day, it's a black and white image. I know I'm showing it in color here, but that's sort of like a temperature heat setting. It's really a black and white image where you're seeing brighter things here and fainter things here. So we could do black and white imaging, and that's 2012. Then in 2014, I went back and got multiple filters, and it's sort of like an RGB image. And then, you know, maybe in 2025, if I'm still with it, we'll have 1,000 images, and it'll be this hyperspectral image. So that's the evolution of how we can study exoplanets. What will we learn with data like this? I mean, it's going to be amazing. You get one hyperspectral data cube like this, and you'll be able to learn so much. I mean, just like that spectrum of the pale blue dot. I mean, there's so much information in one spectrum. So with a data cube like this, the first thing you'll want to know is what are exoplanets made out of? So you'll be able to see all of those individual molecules in each one of these exoplanets. You'll be able to learn something about how these exoplanets form. So if you look at this system, there's a theory that says that the planets that form close in will have different compositions than the planets that form further out, because there's just different stuff in the nebular material that collapses into the exoplanet. So that's something that we'll be able to see right away in a spectrum of this planetary system. You can imagine, you know, looking at this system a few nights in a row and seeing how it changes. And you can use that to infer something about the clouds and the weather on exoplanets. So there's sort of limitless things you can do, even just from one exoplanetary system. Now I want to say that on Keck, there are, you know, right now there's sort of 10 or 20 known bona fide exoplanets. They're more when you include like sort of the super Jupiters and the massive things. We think this new instrument Scales is going to be able to find a lot more. So, you know, maybe there'll be 20 or 30 or 40, which would be super exciting to have that many exoplanets that you could get spectra of. But like I said at the beginning of the talk, you know, the bigger the telescope, the more you can concentrate the light. And if you want to see planets that are really, really close to the star, a bigger telescope is what's going to get you there. So that's the reason that we're building a telescope like the 30-meter telescope. This is a telescope that's not under construction yet, but it's planned. And if you put a Scales-like instrument on the 30-meter telescope, it would be able to see more like 1,000 exoplanets. And to me, that's, as an astronomer, that's really exciting. Stellar astrophysicists, extragalactic astrophysicists, they've got thousands and thousands of things they can look at, and they can compare them in all different ways. And we can't do that with exoplanets yet, but once you can see a huge number of them, you can see, oh, well, do they look different when they're around more massive stars, or do they look different when they're around older stars? And that's the type of thing that you can do when you build up enough of a population like that. Some of the really detailed science that's going to tell us a lot about exoplanets. The next thing you can do with a telescope like the 30-meter telescope is that's big enough that you can, with a lot of hard work, you can image bona fide pale blue dots, things like Earth, rocky planets around other stars. So that's a huge goal. I mean, what could be bigger than that? And then once you can image one of these pale blue dots, you use a technique like hyperspectral imaging, and you get a spectrum of it, and you look for biosignatures, signs of life on the pale blue dot, similar to what you can see on Earth. There's a lot of debate about what sorts of things will be proof of life on these other planets. That's an area of active research right now. But certainly a telescope like this has the capability of looking for signs of life on Earth-like planets. So that's where the field is now and where I think it's going. It's an incredible time for humanity, that in the next 20 or 30 years, we will be able to do this sort of science. And I want to close with a quote from one of my colleagues, Jason Wright, who says, "Of all the topics of study in astronomy, exoplanets hold a special place in the imagination. More than stars, nebula, or galaxy, they are places." And just like titan in our own solar system. There's so many different types of exoplanets that are out there that we're going to be able to study. More types than there are planets in our own solar system, and I'm really excited to find out what they're like. Thank you.
Thank you, Andy. Yeah, we got clapping, lots of clapping in the background if you don't see that yet, Andy. I'm gonna, it's 4:36 and we typically go till 4:45 on the living room lecture. So I'm gonna do about 10 minutes of questions. I'm gonna start with a comment and then follow-up question from a few folks. Sid Har pointed out early on that we were lucky in that situation that the orbital plane was orthogonal to us so that you could see them, right?
That's right.
And Alec asks, are planetary orbital planes oriented randomly throughout the galaxy?
Great question.
If you are not on mute, I appreciate you doing that.
Okay, so the question is, are planetary systems randomly oriented throughout the galaxy? The answer is, we think so. We haven't actually imaged enough to know. But there is this geometric preference, which is that there's only one face-on way that you can get an exoplanetary system, but there are all sorts of different edge-on ways that you can get a planetary system. So you are more likely to see an edge-on planetary system than a face-on planetary system, even if they're randomly oriented.
Great, thank you. And can you talk, Jem asked, what is the most interesting thing that we have discovered from the APF at Lick? What is the APF doing that is different than what you do at Keck? And you might want to talk a little bit here about the KPF.
Yeah, so radial velocity is a complementary technique for studying exoplanets, and we really want them to go together. So those images of exoplanets, unfortunately, they don't have a mass written on them. We can study a whole lot about them, but we don't really know how massive they are. So my dream is to be able to image exoplanets where another technique has determined its mass. And so APF, the Automated Planet Finder at Lick Observatory, HiRes, which is an instrument on Keck, and then the Keck Planet Finder, which is a future instrument that's coming for Keck. Those are instruments that look at the Doppler wobble of the star, and from that infer that there's a mass orbiting around the star. And so all of these systems are really used together. It's quite an interesting ecosystem. Keck can look at fainter objects than the Automated Planet Finder, but unfortunately we have to let extragalactic astronomers use Keck, whereas we don't have to do that with the Automated Planet Finder. Just joking, I see an extragalactic astronomer here. So the nice thing about the Automated Planet Finder is that you can look at the same star every night for a long time. And we think that that's important when you're looking at multiplanetary systems, where if you have one planet, you just need to look a few times to get its orbit. But if you have like a 6-planet system, you need to look many times to figure out all of the different masses. And where I think APF has really shown is basically filling out the catalog of all the different masses of exoplanets, particularly the ones that are transiting. So Kepler and this new mission TESS find these transiting planets. And it's the same thing. You know their radii from transiting. I won't go into that technique too much. But if you get their mass from APF, you get the density. And this huge ecosystem of all of these different instruments is filling out this diagram so that you can figure out the mass versus the radius of exoplanets. That tells you the density. That tells you what they're made out of.
Are there any spectral signatures associated with that planetary rotation?
Which planet are we talking about, or?
I believe the ones that we were looking at before.
The imaging, thank you. Are there spectral signatures with the rotation of the planets? Yeah, so one of the cool things that we want to be able to do is map exoplanets. I didn't talk about that a lot today, but there's a cool little trick you can play when you get to high spectral resolutions, which is that you can imagine that a planet, if you've ever heard of redshift, blue shift, when a planet is rotating towards you, you can see a cloud going towards you and it blocks out the blue side of the planet, the blue shifted side of the planet. When it moves away from you, it blocks out the red shifted side of the planet. And so people have managed to do this now on one or two brown dwarfs. These are free-floating objects that are more massive than exoplanets, but actually look a lot like gas giants. So this is really exciting. We can make maps of exoplanets we can make maps of brown dwarfs, and we want to be able to make maps of exoplanets. I think that there's going to be a talk in a couple weeks by Emily Martin, who's going to be talking about that and how we can tell whether the maps that we make are true.
What spectral artifact would point to possible intelligent life?
Right. So the spectrum that I showed you at the beginning of Earth was not necessarily intelligent life. There's oxygen. There's that red edge. Both of those are telling you about plant life. The methane signature might be telling you something about, I wouldn't necessarily say intelligent life, but at least cows or something like that. So spectral signatures are tough to figure out about intelligent life. There are people that talk about seeing, huge megastructures move in front of stars, and those are called technosignatures rather than biosignatures. Mm-hmm. And it may be that how we figure out that something has intelligent life is totally different than the way that we figure out that it has just life in general.
Paul asked, what are you expecting to find?
Yeah. Certainly, this is a bit of a cop-out, but certainly within this field, it's a discovery field, and you should expect the unexpected. I will say that when I first started taking images of exoplanets, there are a bunch of people who try to predict what they look like, and then you try to match their theoretical models to your actual observations. And when this field was new, and frankly still today, every time you get one new data point, you prove the model's wrong, and then the modelers have to start over again. So I would say we've mostly been wrong so far. When we start to get 1,000 wavelengths instead of 6 wavelengths, we're going to be even more wrong. So I expect certain things about the models are going to be wrong. I don't quite know what those things are going to be. What am I most excited about looking for? I'm excited about looking for water clouds. That's one of the first things we'll be able to do when we have an instrument like this. We'll be able to see really cold planets, really faint planets, and we'll be able to look at water clouds and look for hydrological signatures. And I sort of have no idea what they're going to look like.
Ronan asked, how will SpaceX Starlink impact this effort?
So yeah, SpaceX Starlink, these are these satellites that make these bright streaks through the sky. Those look like they're going to affect a lot of fields of astronomy where you're looking over a very wide field of view. So there's this big new telescope, the Vera Rubin telescope in Chile, which is going to take huge images of the sky, basically making a movie of the sky over time. And because the field of view is so big, it's very likely that a streak is going to go through it and interrupt an observation, which will be unfortunate. For exoplanet imaging, you'll remember I talked about how small it is. The planet's 1/500th of the width of your thumb away. So it's much less likely for one of these streaks to pass in front of an exoplanetary system. So it's probably harmful for some areas of astronomy, but probably not exoplanet imaging.
And last question, Annie. We're just hitting 4:45. If folks don't remember anything else from this living room lecture today, what do you want them to remember?
Wow. All right. I think the thing to remember, while planetary systems are ubiquitous, and we know what we're looking for, it's still very difficult to do it. So this is a technologically driven field, and we're going to have to continue to innovate and build smarter and more specialized instruments to be able to learn everything there is to learn about exoplanets.
Thank you so much, Andy, again, for joining us on Living Room Lectures. University of California Observatories is doing 3 different events series if you haven't had the opportunity to join us. The first one, for those of you who are part of the Friends of Lick Observatory, which is FOLO, we have FOLO family dinners. Then we also have these living room lectures, and then every other week we have Ask an Astronomer. If you live for the end of a lecture where you get to ask astronomers all of the questions. That's your opportunity. Our next one will be next Monday at 4 p.m. You can send questions or learn more about these events to social@ucolic.org, or you can join us on any of our social media sites to ask questions in advance. We have LinkedIn, we have Twitter, we have UCO on Facebook, as well as Lick Observatory on Facebook, and Lick Observatory on Instagram as well. And if you can't get enough of these events, I encourage you to go over to Keck's website, where they have additional really fantastic events, and you'll see a lot of familiar faces from the UC system. Thank you all so much for joining us, and I can't wait to see you next week.